Okay, in this video, we're going to be looking at simple digital logic circuits like the one we see here. Now I'll be using the 4000 series CMOS logic ICs, and these circuits will be very simple. They'll be good for beginners. They'll be inexpensive to build, so all you need is a breadboard, the logic IC, some resistors, LEDs, and push buttons. Now the logic IC I'm using here is a 4081. It's a 2-input AND gate, and there's actually 4 AND gates on this chip. Now one of the AND gates is connected up to this push button switch, and when I press the push button, the LED comes on. So what's so special about this circuit? Well, the output pulse that's feeding the LED is clean. There's no contact bounce on the output pulse. So this is basically a contact bounce eliminator circuit using only one AND gate and one resistor. So this is probably the simplest contact bounce eliminator that you'll find. Okay, here's the schematic diagram of the circuit that I built on the breadboard. Now you'll notice I'm using 2 of the AND gates from the 4081 IC. Now this AND gate here is actually the drive to LED. I'm using it as a driver so I don't pull down the voltage on pin 3. Now this AND gate here, this circuitry here, is what cleans up the contact bounce from the switch. Now you notice on the inputs to the AND gates are connected together. That turns it into a non-inverting gate. So a logical 1 on the input will give you a logical 1 on the output, and a logical 0 on the input will give you a logical 0 on the output. Now if we look at the circuit flow, when the switch is not being pressed, we're having a logical 0 fed into the input here. We'll have a logical 0 here, and a logical 0 here, and the LED will be off. Now when you press on the push button switch and connect these 2 terminals, we'll have a logical 1 on the input, a logical 1 here, and a logical 1 here, which will turn on the LED. So how does this circuitry here clean up the contact bounce from the switch? Well, the key component is the resistor here. This resistor is connected from the output of the gate to the input, which causes it to latch. Now when the button is being pressed, we have a logical 0 coming up to the gate, and that logical 0 is fed back into the input. So we have like a dog catching his tail. It latches up this IC. So no matter how much this contact chatters, this will always be a logical 0. Until we press the switch all the way down and we connect these 2 terminals. Now we'll have a logical 1 here, which will go through and be fed back. Now it will latch up into a logical 1 output. So no matter how much these contacts bounce, this will always be a logical 1. So that's how it takes care of the contact bounce. It causes this gate to latch either into a 0 or a 1 output, and you won't get any chatter going out to the LED. So why are we using a resistor? Why can't we just use a jumper? Well, if we put a jumper in here, and now when the switch isn't being pressed, we have a logical 0 coming into this point here. Now there's a propagation delay for the logical 0 to go through the gate. It's about 25 nanoseconds. So now when we press down the switch to a logical 1, this point here will be logical 1 right away before the propagation delay. So we'll actually be putting a logical 1 into a logical 0 when we get a little short. We'll have a short here for about 25 nanoseconds. So this resistor is a current limiting resistor for the short circuit. So with that resistor in there, we don't have any heavy currents being fed through the gate, the output of the gate, and could cause damage to the gate. So that's how that circuit works. Now when we press the switch up and down, we'll get a nice clean signal and output. So this circuitry, it's very simple, but there's a lot happening. There's a lot going on. Okay, I have my scope hooked up to pin 3 of the 4081 AND gate IC, and I pulse my push button. You can see I'm getting a nice clean positive pulse. The edges are clean. I'll pulse it again. You can see every time I pulse it, I get a clean pulse. Now if I remove the 22 kilo ohm resistor from the circuit and pulse it again, you can see I'm getting contact bounce on the edges. So if we would feed this signal into a counter, we would get erratic counts because of the contact bounce. Okay, now you know how this little contact bounce circuit works, but it's the concept I wanted to get across. The concept that you could take a non-inverting gate and turn it into a latch just by using a resistor and connecting it from the output to the input. And why we're using a resistor? Because the signal through the resistor is faster than the propagation delay through the gate, and we get a momentary short. So you can take that concept that we learned here and use it in your own design. Okay, here's my next simple logic circuit, and I'm using the same IC, the 4081, which contains 4 AND gates. I've added a toggle switch and a diode. So when I press my push button switch, the LED comes on. So this could be like a little alarm circuit. An LED could be like a buzzer. And when I trigger the alarm with the switch, it could activate the buzzer. Now if I want to go into a latching mode, I just turn on my toggle switch. Now when I press the push button once, it latches and the LED stays on no matter what I do with the push button. Now to turn off the LED or turn off the alarm, I have to turn off my toggle switch back down to normal. Now it's back into normal mode. Now if I want to latch it, the latching option, I just toggle it, and one pulse, she latches it. Now I'm only using one AND gate to do this for the latch function. Now all the rest of the AND gates that I'm not using, with 4000 series CMOS logic, you have to tie the unused inputs either high or low, and you can see that here. The unused gates that I'm using, I'm tying the inputs high. So we'll have a look at the schematic on how this circuit works. Okay, here's the schematic diagram of the circuit that I built on my breadboard. Now this circuit is very similar to the last circuit that we looked at. Now I'm using two AND gates in the 4081 IC. Now this second AND gate here I'm using as a driver to drive this LED. So I'm giving some isolation to this AND gate so I don't pull down the voltage on pin 3. Now this AND gate and the circuitry around it is responsible for the logical function of this circuit. So when the toggle switch is open and the push button switch is open, this pull down resistor will feed a logical 0 into the input of the AND gate, and that logical 0 will be filtered through the string and keep the LED off. Now when I press the push button switch, we'll get a logical 1 fed into the input of the AND gate, and that will be filtered through the string, and it will turn on the LED. So every time I press the push button switch, the LED will come on. Now when I close the toggle switch and put it into the latch mode, now when I press the push button switch, we'll get a logical high onto the input of the AND gate, and that will be fed back into the input, and it will latch this AND gate to a logical 1 output, which will turn on the LED, and the LED will be latched on. The only way to turn off the LED would be open up the toggle switch, and now the pull down resistor will feed a logical 0 through the string and turn off the LED. Now we need this blocking diode in here, because when we push the push button switch, the logical 1 would get there first before it has a chance to propagate through the gate, and we get a short. So this blocking diode keeps the short from happening. So that's a little circuitry there. It's pretty simple. So this is a little example how we could do more with less with a very simple circuit. But this is part 1 of this series, and in part 2 I'll be doing a circuitry on monostable circuits and some clock circuits. So stay tuned for part 2 for simple digital logic circuits.